Hello everyone, my name is Dan the Tutor. This is a clip from one of my weekly group tutoring sessions at the University of Delaware for Physics 201. If you have any questions, please leave them in the comments below. Thank you and enjoy. So let's go ahead and jump into the first problem here. A helicopter's blades reach an angular speed of 400 RPM in 20 seconds. What is the angular acceleration? And then how many full rotations do the blades complete after 20 seconds? So for this problem, the first thing I'm going to do is I'm going to see how many of these variables I know. Omega initial, omega final, alpha, time, and delta theta. It doesn't say it in the problem. I probably should have mentioned it, but we're assuming we start from rest, which means angular velocity 0. Now, the final angular velocity, or angular speed, because remember, speed is just a velocity without a direction. In other words, we don't care about the plus or minus, which I'm just going to tell you I don't care about the plus or minus right now for the next while. But it says 400 RPM. 400 RPM. In other words, I'm going to rewrite this as rotations per minute. Rotations per minute. We do not like rotations per minute in physics. We like units of radians and seconds. So in other words, I'm going to have to multiply 400 by some kind of combination of variables here to get me back to radians per second. So if I'm starting with 400 rotations per minute. Let's start with converting minutes because that's actually easier. And I'm going to say in 1 minute there's 60 seconds. This is called dimensional analysis, where we pretty much cross off the units just like this. Minutes has to be in the numerator, and there's 60 seconds in the denominator. And then how do we go from rotations to radians? Well, whether it's rotations, revolutions, or just complete paths around a circle, I'm going to put one rotation in my denominator. And how many radians are in one rotation? How many radians are in a circle? The answer to that question is 2 pi. So we multiply by 2 pi radians over one rotation. Rotations will cancel out. We're going to be left now with radians per second. So now I'm just going to multiply this across in my calculator. It's 400 times 2 times pi divided by 60. We're going to get a final angular speed of 41.89, let's say. 41.89. And again, the units are radians per second. Let's finish up this question. We have 41.89 radians per second. I'm saying this is my omega final, my final angular velocity. Let me go back to this page. So omega final is 41.89. And again, the units are radians per second. Okay, alpha, angular acceleration. That's what I'm actually asked to solve for, so I'll put a question mark there. Time, they tell us it's 20 seconds. And delta theta, how many full revolutions do the blades complete after 20 seconds? So there's two questions I'm being asked to solve for. First, I'm going to find alpha, then I'll find delta theta, which is the other part. So if I want to find alpha, notice I do have 3 of my 5 variables. 1, 2, 3. It means there is an equation I can plug into. Now, if this were linear motion, linear kinematics, I would say that equation is v final equals v initial plus acceleration times time. Except we don't have those variables here. We have their angular counterparts. In other words, we have omega final equals omega initial plus alpha times time. Did I lose anyone so far? Okay, good. So then omega final is going to be 41.89. That's equal to omega initial, which is 0, plus alpha, which is unknown, times a time of 20 seconds. So I can just plug this in my calculator, divide by 20. Alpha is going to be 41.89 divided by 20. It's going to be 2.09, and the units are radians per second squared. Okay, there we go. We found alpha. Now, how are we going to find delta theta, the number of revolutions? Well, remember, delta theta is actually measured in radians. Like if I were to plug into a formula, I find delta theta, I'm going to find radians, I'm not going to find revolutions. That's a problem because the question's asking us to find revolutions. So how do I do that? Well, first let's just find the number of radians, and then just like how we converted from revolutions per minute to radians per second, we're just going to go in the opposite direction. We're going to convert from radians to revolutions. So which equation should I plug into? I'll just tell you. It's going to be delta theta equals omega initial times time plus 1/2 alpha times squared. There's actually a couple correct equations at this point since we have pretty much all the variables, but this one will work for us since we just found alpha. So delta theta equals omega initial times time, which is 20. That won't matter because it's just times 0, plus 1/2 alpha. We just solved for it. It's 41.89, and then time squared is 20 squared. So all I need to do is plug this in a calculator. We're going to get delta theta 0.5 times 41.89 times 20 squared. We will get a final delta theta of 8,378. Again, the units are radians. It's not revolutions. In other words, this is not our final answer because I want to find revolutions. How do I convert this to revolutions? Well, as we did before, I'm going to multiply by something with a fraction bar here. In the denominator, I'm going to have radians. In the top, I'm going to have revolutions. And by the way, revolutions and rotations, I'm going to use them interchangeably because they are interchangeable. They mean the exact same thing. A rotation and a revolution is the exact same thing. And then I say to myself, in one revolution, there are 2 pi radians. That's the correct factor. So radians cancels. We're left with revolutions. I just need to divide my answer by 2 pi. So 8,378 divided by 2 divided by pi. And we are going to get a final answer of 1,333.4 revolutions. Now careful here, if you look back at the original question, I said, how many full revolutions do the blades complete after 20 seconds? In other words, full rotations, 1,333 revolutions. And that's the answer to the first one. Let's go on to the second one. It's going to be another rotational kinematics problem. A generator is rotating at 30 radians per second before it gets shut down and comes to a halt. It slows down with a constant angular acceleration of negative 7.5 radians per second, which, radians per second, that's just radians per second squared, really. And the fact that it's negative really just means that it's slowing down here. That's what the negative sign means. So then the question, how long until the generator comes to rest? And then the other part, how many revolutions does it complete? This time we can round to the nearest whole number. So it's going to be a very similar problem from before. I'm going to first write down my omega initial, omega final, alpha, time, and delta theta, and ask myself what I know. So this time, if I read the question, it was initially rotating at 30 radians per second. In other words, omega initial, omega initial is going to be 30. Omega final, well, it says it's slowing down to a stop or a halt. So I know omega final is going to be 0. Alpha, they tell me it's negative 7.5 radians per second squared. I'll ignore the units right now. And we want to find time, and we want to find delta theta. Okay, great. So again, we have 3 of our 5 variables, which means we can plug in and solve for time, or delta theta. Let's start with time. It's actually going to be the exact same equation from before. Omega final equals omega initial plus alpha times time. Go ahead, I'll give you 30 seconds to solve this on your own. And then I'll be doing the work on the screen right now in the meantime. And hopefully you got the same answer as me, or if you didn't get it yet, you're probably close, hopefully. The time is going to be 4 seconds. So all you had to do was plug in the values here in the right spot, and then it was just algebra. Pretty straightforward. So time of 4 seconds for this first part. The second part of the question, how many revolutions does it complete? Round our answer to the nearest whole number. So again, we're going to be solving for delta theta, which is going to be in radians, and then we need to convert to revolutions. So I want to use a different equation than the one we used last time just to show you different ones work. Let's use the equation that doesn't have time in it, which is omega final squared equals omega initial squared plus 2 alpha times delta theta. It's extremely similar to the one that we saw back at the beginning of the year where we had v final squared equals v initial squared plus 2a delta x. except this time we're literally replacing all our variables with their rotational counterparts. So omega final, that's 0 squared, equals omega initial, 30 squared, plus 2 times alpha is negative 7.5, and delta theta is going to be what we're solving for here. Okay, so let's solve this. The left side's just 0, easy. 30 squared is 900, and then 2 times negative 7.5 is negative 15 delta theta. Add 15 delta theta to both sides, and then I can't do this in my head, but 900 divided by 15 will be 900 divided by 15. Still a round number. Great. 60, but not revolutions, radians. Now, how do we convert radians to revolutions? Exactly what we did before. We're either going to be multiplying by 2 pi or dividing by 2 pi. I want you to take 5 seconds on your own to think about that while I write this. So I'm saying radians is in the denominator, revolutions is in the numerator. In one revolution, there are 2 pi radians. We want to divide by 2 pi. So 60 divided by 2 divided by pi, that's going to give us 9.55. And again, the units are revolutions. This time they wanted us just to round to the nearest whole number, so I'm going to say 10 revolutions for this one. Any questions on this one? Now there is one more.
Yeah, I got.
Oh, go ahead.
Sorry, I got 94.24 for that.
Thank you, because you literally just pointed out the point I'm going to make right now. You have to be very careful when you plug this in your calculator, because if you put 60 divided by 2 pi, just like how I said it, your calculator is trying to multiply by pi. You need to put another division sign. So go ahead and try that and tell me if you get this answer.
Yeah, I got what you got now.
Yep, and that's the killer of these questions, is exactly that right there. So thank you for asking that question. That was a good question. Okay, and that's it for number 2. Number 3 is, I'm going to say, significantly more difficult. Let's talk about it. A bicyclist's tires increase in angular speed from 12 radians per second to 18 radians per second in a time of 5 seconds. They then maintain that speed for another 10 seconds. How many revolutions do the tires complete in the full 15 seconds? And then there's another part. If there is a piece of gum stuck to the edge of one of the tires and the tire's diameter is 0.7 meters, what is the tangential speed of the gum after 5 seconds? Okay, so we're going to break this up into 2 parts. The part with the piece of gum, that's a completely different topic that we haven't talked about yet, but we will in 5 minutes. Okay, so for this question, what I'm going to say is it starts out exactly the same. Omega initial, omega final, alpha, time, and delta theta. They even give us a lot of the information. It started at 12 radians per second, ended at 18 radians per second, and they set a time of 5 seconds. And then they're asking, actually there's another thing I need to mention here. They give 3 times. They give 5 seconds, 10 seconds, and 15 seconds. So it's really important to read this question carefully and understand that this journey that the bicyclist is taking, can be split up into 2 parts. The part we're looking at right now is for the first 5 seconds, and then we're going to have to do another equation for the last 10 seconds. Then we're going to add the 2 answers together. That's how you get the full 15 seconds. So let's take it one step at a time now. At 5 seconds, so t equals 5, we are solving for delta theta. We don't even need to find alpha for this problem, it looks like. And luckily we do have an equation here that we can use to find delta theta. It is the following. Delta theta equals 1/2. That's supposed to be a 2. There we go. 1/2 times omega initial plus omega final divided by time. I'm sorry, times time. My bad. Times time. There we go. So it's this equation right here. Now let's go ahead and plug in everything we know. So delta theta equals 1/2 times omega initial is 12 plus omega final is 18 times a time of 5 seconds. We can just plug this in a calculator. 12 plus 18 is 30. 30 divided by 2 is 15. 15 times 5 is 75. And that's, again, radians. Now, we were asked to solve for revolutions, as is very common. Like, I'm not just doing that to be annoying. It's very common to ask for revolutions, not radians. So I just want us to get in the habit of doing that, because it's going to be so often that happens. So 75 radians. Again, I'm going to divide by 2 pi radians in the numerator, 1 revolution or 1 rotation. It's the exact same thing. So 75 divided by 2 divided by pi. We're going to get 11.9, and that's revolutions. I forget what I said, if we want to round or not, but it doesn't matter since this is only this is only half the answer anyway. To find the full answer, we need to know what's going on in the last 10 seconds. So I'm going to tell you for this, if you write down omega initial, omega final, alpha, time, and delta theta, and the only thing that changed is the time is now 10 seconds instead of 5, this is the wrong way of doing it. And let's talk about why that is. I'm going to scroll back up to the question. It says, we just read the first part for 5 seconds. Second part, they then maintain that speed for another 10 seconds. Question, what is the initial and final velocity for the bicyclist for the last 10 seconds? It's going to be 18 radians per second. It stays at 18, okay? And because of that, the angular acceleration is actually 0. Why is that important? It's important because if you do this method and you use the 5 variables, there's not a single equation that's going to work out for you because omega initial equals omega final and alpha is actually 0. I'm going to write that down. Alpha equals 0 because omega initial equals omega final, and they both equal 18 radians per second. If you try and plug this into any of your equations, you're just going to get a nonsensical answer. You can even try it on your own if you don't believe me. What I'm going to tell you, though, is we're going to use a different equation instead, and that equation is just very simple. It's omega, either the initial or the final, because they're both the same. Omega equals delta theta over time, and we can do this because it's constant speed. Constant speed, or constant angular speed in this case. And this was true back in kinematics when we were dealing with linear kinematics, and it's going to be true now as well. So this happens, I don't know how often it happens, but it's a good thing to know, definitely. We know omega, it's 18, delta theta is what we're solving for, and the time is 10. Very simple, delta theta is equal to 18 times 10, it's going to be 180, again, that's radians. So we do need to convert from radians to revolutions again. Let's do that here. 180 radians times 2 pi radians in the denominator, and then 1 revolution in the numerator. 180 divided by 2 divided by pi, we get 28.6, and that again is going to be revolutions. So I forget what we got for the other part. It was 11.9. So I'm going to add 11.9 plus 28.6, and that's going to give me the total number of revolutions. 11.9 plus 28.6. I got an answer of 40.5, and that's revolutions. I don't care what well, actually I should care. Let me go back to the question and actually see what I was asking, because it is important to actually check that. So it says, where is it? How many revolutions do the tires complete in the full 15 seconds? So how many revolutions? You could argue that since it says that it complete revolutions, that would only be 40. So personally, if I were a professor, I would accept both 40 and 40.5 because I don't think I'm very good with the wording in this question. But always read the questions carefully is the moral of the story there. And actually, we're not done with this problem yet because, as I said earlier, there is another part, and that is the following. If there is a piece of gum stuck to the edge of one of the tires, and the tire's diameter is 0.7 meters, what is the tangential speed of the gum after 5 seconds? So this involves another equation, and this equation is extremely, extremely important, especially on the final. And if there's, I don't know if you guys have one more midterm before the final, but it's going to be on it if you do have one. And that equation is the following. Tangential velocity, Vt, is equal to omega times the radius. In other words, I'm going to write out what each of these things says. Tangential velocity. What is tangential velocity? That's if you had the speed gun kind of velocity, okay? Is equal to omega, which is angular velocity, which is not like speed gun velocity. It's more like how fast are you rotating? Just how fast are you rotating? And then times the radius, which is r. And this equation right here is so important because it's never going to tell you explicitly that you need to know this equation. This equation you need to have in your back pocket ready to pull out at any moment, because if you don't, then you have no hope of answering this question. So let's go back to the question. If there is a piece of gum stuck to the edge of one of the tires and the tire's diameter is 0.7 meters, so right there they're telling us the radius. The radius is 0.7 divided by 2, which is 0.35 meters. And then it's asking what is the tangential speed of the gum after 5 seconds. So they're asking us to find VT, the tangential velocity. We know the radius, it's 0.35. And if we know omega, the angular velocity, then we're good. And good news, we do know the angular velocity at 5 seconds. I'll give you a few seconds to think about it. What is the angular velocity at 5 seconds? Well, at 5 seconds, that was the final in our first 5 seconds, if you think about it. So at 5 seconds, its angular speed is going to be 18 radians per second, which means times 18. The 0.35 times 18 is going to be our final answer. 0.35 times 18. We get 6.3, and the units are meters per second. Now, I do want to take a second to talk about units, because this almost makes no sense, and let's talk about why. So, velocity is meters per second. I'm just going to write the units right now. Velocity is meters per second, radius is measured in meters, and angular velocity is measured in radians per second. So technically, shouldn't it be meters times radians divided by seconds? In a way, yes, but more importantly, no, because radians is more of just a placeholder unit, and it also signifies circular motion. But here's the thing about tangential velocity. Tangential, even though we're moving in a circle, you don't have tangential velocity at any one point, because just look at this. Well, if I were to draw this line right here, angular velocity isn't a circular motion, right? Angular velocity is. But tangential velocity, no matter where I draw the tangential velocity, notice it's only pointing in one direction. And that's because velocity doesn't go in a circle. Velocity just points straight ahead. And it's constantly changing at every point in time, so that together the velocity moves in a circle, but at each individual point in time, it's not. It's a straight line. Kind of a weird concept to understand, but that's why velocity is meters per second and omega, angular velocity, is radians, because we're moving in a circle. Any questions on that? Don't forget to like and subscribe. If you want me to start doing free weekly group sessions at your university, please post in the comments below or email me at dan@danthetutor.com. Thanks everyone. Bye-bye.